Okay, so first I'll talk about energy units because that's kind of straightforward. And our common units of energy, our official or SI unit is a joule, which is J, or a kilojoule, which is 1,000 joules, is a kilojoule. Put this over there. We also have a calorie, little c, or we have a kcal, which is a capital C calorie. So here's something that's tricky. This one's probably easier to see. Let me zoom in on this juice box. This is a really subtle difference, right? A lowercase c or a capital C. That's a capital C. This is actually 90,000 calories. Yeah. Nobody wants to buy a 100,000 calorie pack. That doesn't sound healthy. So there's a little trickery involved here. The calorie on your nutritional information is actually a kcal, right? So 90 calories equals 90,000 little calories. Tricky, right? One of the questions that they use to stump kids, it's one of those questions that like Jimmy Fallon asks people on the street, like, if you eat 2 pounds of food, does that mean you lose 2 pounds the other way? And you don't, right? It's not mass in, mass out. Why? Well, that would still be mass, right? If you're taking in the nutrients, you would still, those atoms would still have the same mass, whether they're incorporated into a cell or whether they're excreted by your body and you weigh it. What happens to the mass of your food? Why don't, if you eat 2 pounds of food, you don't excrete 2 pounds? I just told you, this is a unit of energy. But you would still have that mass. It's not just distributed. The matter is converted to energy. It's converted to energy, which kind of breaks atomic theory, right? That matter is conserved. So, just a note, matter can be converted to energy. See chapter 23. We'll get there at the end of next semester. Okay, so just kind of a glimpse of things to come. But that's one of those questions they love to ask people on the street because most people don't think of it in that way. But your clue is that it's a unit of energy, right? It's a unit of energy on your nutritional value. Okay, so I want to talk about, those are the main units of energy. And you don't have to memorize this, but 4.184 joules is 1 calorie. You don't have to memorize, but just to kind of give you a point of reference. A calorie is important because it's the specific heat of water. So the specific heat is the energy it takes to heat 1 gram of something by 1 degree C. And for water, it's 1 calorie or 4.184 joules. That's why it's important. Okay, so I want to talk about kinetic versus potential. What do you think of when I say kinetic energy? We'll do a little word association, keep it clean. Kinetic energy. Yeah, motion, right? Right on. We're talking about motion. Maybe you're thinking about speed or velocity as well. You might have that association. What about potential energy? What do you think about? Yeah, it builds up. That's a good one. I like that. I usually think about the boulder at the top of the hill, right? Something that has high potential energy is some rock at the top of the hill because of gravity, right? Because of gravity, it wants to roll down. A better way to think about potential energy, and this is simple, but it's so important, it's the energy of position. Potential energy is the energy of position. And we're going to use this to solve a lot of problems, because when we talk about bonding, all bonding is the attraction of opposite charges. That's all it is. Even a covalent bond, the electrons of one atom, the valence electrons are attracted to the positive nucleus of the other atom. So the energy of position. So we're going to work with some basic definitions. High potential energy means that the objects or point charges or whatever are not in their desired position. Just like the boulder at the top of the hill wants to be at the bottom because of gravity, that's high potential energy because it's not in the desired position. So low potential energy means it is in the most desired position. That's the lowest energy. Okay. When we talk about kinetic energy, I'm going to scooch back, I forgot. Kinetic energy and motion. This is so intuitive, you're going to laugh. You already know this. Okay, let's think about the three phases. Sorry, plasma. Let's think about solid, liquid, and gas. Let's think about particles of matter in these different phases. And think about kinetic energy or motion of atoms. Atoms are always in motion in every phase. Okay. So thinking about the different phases, solid, liquid, gas, and thinking about average particle motion, which phase do you think has particles with the highest kinetic energy? Right? It's intuitive. So highest kinetic energy or motion. So solid, lowest, right? The lowest kinetic energy or motion. That's intuitive, right? We're going to slap a fancy name on that. It's called kinetic molecular theory. I think we just grew a couple of brain cells just by saying that. Kinetic molecular theory is just that. Based on the phase of the particles, you can predict the relative average motion. And you already know that. It makes sense, right? That makes sense. All right. That's about all we're going to do with kinetic energy for now. I got so excited I jumped right to potential energy. I am really excited about it because this solves so many problems. We use these concepts to talk about electron affinity and ionization energy, and we use these really simple ideas, this very simple idea, to answer a lot of problems. So I'm going to draw a couple of scenarios, and I want you to predict if it's high or low potential energy. So I'm going to draw two positive charges in close proximity. I'm going to do one positive and one negative in close proximity. I'm going to do two negative charges and just far apart, whatever that means. These are all relative. And then a positive and a negative far apart. And I want you to spend about 2 minutes labeling these as high or low potential energy using this definition. High potentially, no, they're not where they want to be. Low potential energy, yes, that's where they want to be. All right, so let's spend 2 minutes. You guys label that, and then we'll go over that. You can talk to each other. It's allowed. So you do need one piece of information to solve these problems, and that is how do like charges interact with each other. So same charges, they repel. So like charges repel, opposite charges attract. Okay, so if opposite charges attract and they're close together, is that where they want to be? Yep, so that's low. Same charges together, is that where they want to be? Nope, so that's high. I used to bring in my son's little magnetic train set, but he's a big boy now. Same charges far apart, is that where they want to be? Yes, they repel, so they want to be far apart. So this is low potential energy. Opposite charges far apart, what do you think? High, that's not where they want to be. They want to be together. Okay, awesome, awesome.